So, I'm scared. I do not remember any of this.
Work not conserved?
No, just no. I don't remember how to do it.
I started playing a lot.
Oh man.
So what?
I played one time.
You know what? Just not going to use these. I think that was my plan when I did that. All right. So there's, oh really? There is work non-conserved. There's the definition. All right. So if you check this out, guys, quiet down, please. The quicker we get through this. All right. So work non-conserved. The mechanical energy that is lost or gained when other non-mechanical forces act on a system. All right. And these are a lot of different forces. So we'll talk about friction, air resistance, and any other external forces. Okay. All right, so when we only use gravity and springs, we're just going to use mechanical energy initial equals mechanical energy final. However, when there is other forces acting on it, we have to consider the work non-conserved equation. So it adds just one extra little thing we got to consider, which isn't too bad. I mean, what's the difference from 6 to 7? 1, yeah. It's just, it's not that bad.
Well, because 7, 8, 9.
Yeah, we're not getting this. We're not getting the 8. I know.
Is 1 alive?
Is 1 alive?
No, like a lot.
A lot? I mean, no.
Depends on what you're counting.
Depends what you're counting. All right. So everybody got that? Still going. So we're going to look at some examples of how we involve work non-conserved. Okay. We good? All right. The first example says you push a 2-kilogram block initially at rest. Initially at rest on a frictionless surface with 10 newtons of force horizontally for 5 meters on level ground before letting it go. The block slides into a loop with a radius of 0.5 meters. What velocity will the block have at the top of the loop? All right. So what we got to consider here, we got to write down everything we know. All right. So what I'm going to do, I'm going to put this up here so we can see it. Shine bright. All right. I'm going to zoom in real quick. Yeah.
Click the little hide button on that.
That's a great idea. Let's do that. All right. Would it be easier if I turn my light off?
Yeah.
Can you get that? Just the, yeah. Do the right one first. We'll see how it looks. What do you guys feel? I'm feeling both off. We can probably do both off. Is that good?
Sure.
Fair enough. I get that. All right. So once again, my equation we just wrote out was mechanical energy initial plus the work non-conserved is equal to my mechanical energy final. Now, I'm going to zoom in a little bit. Now, you don't have to write all this down unless you really want to. So mechanical energy initial is my kinetic energy initial plus my potential energy initial plus my elastic potential energy initial plus my work non-conserved is equal to my kinetic energy final plus my potential energy final plus my elastic potential energy final. Hot dog. Seven units. There it is. Seven different things. Now, if we look at this, first of all, is there a spring involved? No, there's not. So we can automatically get rid of my two elastic potential energies. Okay?
Now we're down to 5.
Say what?
Now we're down to 5.
Now we're down to 5. Do I have initial kinetic energy? No. Down to 4. All right. You push it to initially at rest on a frictionless surface with 10 newtons of force horizontally for 5 meters. All right. So do I have initial potential energy?
Yes.
I do. Not on level ground. I shouldn't have potential energy. Down to 3
Wait, what was the reason for
on level ground.
Oh, I got it.
So mass times gravity times
that?
height. So if height's 0. Hey, so I'm down to 3. All right, I can do 3. 3's not too bad. So let's look at these. Work. What's my work equation?
Displacement times
Force times displacement times cosine of theta.
Okay, I like that. Force times displacement times cosine of theta is equal to my kinetic energy final equation. All right, so my kinetic energy final, so that's half the mass velocity squared plus my potential energy, which is mass times gravity times height. Okay, any questions so far? That's like half the battle, is just determining that. It's a great song. Great song. All right, so let's plug in the value we know. All right, so our force we're applying is 10. What's our delta x? How far do we move it? 5 meters. Times the cosine of theta. Now, we're pushing it, and it's going the same direction. So what's our angle? 0. Okay, so there's that. Is equal to half the mass. My mass is 2. Velocity squared. I don't know that yet. Plus mass, which is 2, times gravity, which is 9.8, times the height. Okay? So if the radius is 0.5, let me go back to our slide. If our radius is 0.5, what is the height of the loop? 1. Should we be able to solve for v squared? Plug it all in. Hopefully. Let me know what you get. Anybody get an answer? 6 is what I got as well. You guys getting that? Okay. Yeah.
Would it be negative 6 because now that it's showing it's at the top of the loop, so it's changed direction. So now it's traveling the opposite direction.
What is the velocity at the top?
Because the loop says it's turned around 180 degrees.
What you're saying? It is going backwards. Now, if it's at speed, yeah, you can put -6. I'd say that's right. Because it's going backwards. Because if you're going around the loop and you're on the top of the loop, but when you're at the top of the loop, you're eventually coming back around.
Yeah, but see, at that point, in
At that
time,
point, I see what you're saying. So negative would represent you're going backwards.
when it finishes going around the loop.
I feel like after that point, like right after the top, any time after that, well, not really. Any time after the 180 degree angle. So anytime like you're west, coming back down would be positive. Wait. So let me draw it. So if you're on, here's your loop. I'd say here is positive. This would be positive. This would be negative. This would be negative. This would be positive.
Wait. Okay. Can I draw this out real quick?
I'm on board?
Yeah.
I mean, if you want.
Okay.
Markers are right here.
Wait. Okay. So. Okay, so it's negative going right here, right?
Yep.
So it's negative right here, but at the very top. So that's where, I don't know how to explain it, but at the very top is, this at the very top?
Yeah.
So if it's at the very top, then it isn't negative or really positive because this is where it goes positive right here.
That's still
But that's
negative.
going
Oh yeah,
backwards.
it's still negative, so right here. So it just seems like, well, if it's at the very top, it's not really.
You're still going up.
Yeah, no.
Yeah.
It's moving to the left.
Yeah.
So like from
Up or down
So-
doesn't matter.
Doesn't matter.
doesn't matter that much. But
Yeah.
I'd say like from right here, that's where you start to move left. And like here, you're still moving left until here. So right here is when it will turn positive, and here will still be positive.
Okay.
Because all that you're still moving.
But okay, I don't see how we like. If you don't give us a picture, I don't see like how we could really.
Granted, you would probably have a picture. All right. Let's see. Next question says, what is the max height the block will reach? All right. Once again, I'm going to write out everything. You do not have to write out everything unless you want to. All right. So I have the kinetic energy initial plus potential energy initial. Go over. Plus the elastic potential energy initial plus the work non-conserved is equal to the kinetic energy final plus the potential energy final plus the elastic potential energy final. Okay. So what is the max height the block will reach? Okay. Now, max height, will I have kinetic energy in the initial? Nope. So once again, kinetic energy initial, potential energy initial is going to be 0. Elastic potential energy is still going to be 0. Now my finals is going to change a little bit. Will I have kinetic energy in the final? No, it's going to come to a stop, which means still no. So all I have is work non-conserved. So once again is 10 times 5 times cosine of theta is equal to potential, which is mass times gravity times height. Okay. Or that's cosine 0. Cosine 0, right? So all we have to do is solve for h.
Yeah, we are gonna need a picture because it's just going in a loop from what it says here. It does not say that there's like that ramp sort of thing after it. In the question.
Magical.
Yeah, that works.
So just knowing that the loop is there, that's it, then the max height would have to be 1.
So when you,
That's the highest.
all right, so when you have this, this is what the picture would look like. What would the max height? What is the max height? So you are pushing it this way. You're going around the loop.
Oh, you're pushing that. Okay, that makes sense.
Force applied.
I thought you were dropping it on the left. That's why I was super confused when you said it. I was like, wait a minute.
So you're pushing it this way. You're going to see.
It would be positive then. Velocity would be positive then if you don't have
Yeah.
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 Based
So
on
this
the-
keeps on. Why do we overthink?
Based on the picture, I guess it is positive.
So, what if we look at it from the other side?
But we're
So,
not. That's
we're
the
not.
picture.
Wait, you guys look at
Pushing it
this.
from this way?
Apparently,
What is the max height? Does that make sense? So you're pushing it, goes around the loop. What's the max height? Does that make sense?
Yes, now. It's
Now
30.
it does.
why do we not have a diagram?
It's 30.
So what's your max height?
30 meters.
2.55.
Which is
I got
3 meters.
It's only this time somewhere.
Yeah,
I don't think
you gotta get rid of the 0.
Me?
I think so.
Hold on.
You definitely.
Turn that.
Will you get the angle of the
Oh, I just didn't.
No,
I
it's an imaginary
subtracted.
speed.
No problem.
All right.
Yeah, I did 50 minus 19 times.
Fair enough. All right. We feel good. Let's do another one. I'm gonna leave the picture up there.
Okay,
idea.
Thank God.
Like I thought it'd be easier if I could zoom in on this just alone so you could see that a little better, but all right. So I'm gonna do is zoom out. All right. Deep in the forest, a 0.0175, 0.017, I don't know why I said 5, kilogram leaf falls from a tree and drops straight to the ground.
Oh.
well, they're there to diagram it, so they must.
If its initial height was 5.3 meters and its speed on landing was 1.3 meters per second, how much non-conservative work was done on the leaf?
Okay.
Mr. Bowers, it kind of makes me sad that there's no storyline to this one.
Yeah, there's no story on these.
It was kind of hard to.
It's the journey of a week.
No, like the entire
No, the
chapter.
entire thing.
We like the drama in the past. They made it
Like
more
rolling
memorable.
and Jonathan.
Can I make a special request?
Carl from chapter 1.
How do you remember that?
Wait, Carl was the box.
Carl
No,
was
it's
last
the girl and the guy.
The girl and the guy, I
Yeah,
forget their names.
Was it Jimmy and Bing?
No,
No,
Jim.
no.
Jim and Cindy.
Jimmy and Cindy, that's what it was.
And Harry, that was the third.
Oh, Harry.
Oh, man.
Good times.
All right, so I'm just writing all this out again so we can evaluate it. Kinetic energy final plus potential energy final plus elastic potential energy final. All right, a lot of things in this. I'm going to zoom out so you can see all the things. There we go. All right. So, reading this, deep in the forest, all right, do I have initial potential energy when it's like
Yeah.
sitting there?
Yes.
Yeah. Okay, so I have potential. Do I have kinetic?
No.
Not quite. Not in the initial. Is there any springs involved?
No.
Okay, so I can get rid of both elastics. Okay. Work non-conserved. Is there potential energy while it's falling?
Yeah. Wait, when it hits the ground, no.
When it hits the ground?
When it hits the ground, it doesn't have it.
Or no potential. All right. So all I'm left with is potential energy, initial. So initial, I have mass times gravity times height. My work non-conserved is what I'm solving for. I don't know what that is. It's equal to, my kinetic energy equation is half the mass velocity squared. Okay, so let's plug in the numbers we know. Mass, we know the mass is 0.017. Do we know gravity yet? I feel like that's just going to be engraved in your brains for the rest of your lives.
But now I'm going to question, is it negative or positive?
That's a great question. The height. The initial height was 5.3. I don't know work non-conserved because that's what I'm solving. Half the mass, 0.017. Velocity squared. My velocity is 1.3. And I should have
enjoy this. Now this I enjoy.
No.
I should have all my information. So you should be able to solve for work non-conserved now, right? The picture definitely helped a little bit. I'm just kidding. We probably could have solved it without the picture on this one. You got an answer for work?
Can work be negative?
No,
No.
just say no and get over it. Please.
So work is equal to force times the change in displacement.
Hold on, just can work be negative in this chapter? That's a
Let's
question.
focus on this
Well, you
chapter.
could, 'cause
Work is equal to
cosine of
force.
theta, you can have a negative.
X equals M.
Can cosine of theta create a negative?
Yeah.
Really?
Yeah.
Wait, and so in this thing is
What's that?
Yeah, so
All right, so you can have negative work. I was thinking cosine of 0 is 1, cosine of 90 is 0.
Displacement's also
I didn't know what cosine of 180 was.
The
It's a negative
the
1.
displacement's also negative.
sine
The other
equals y cosine.
So what did you guys get for work? I assume you got a negative.
Negative 0.868615.
8686. So I like that. Is that close to what we got previously? Yeah, very good. Very good. Okay. What time is it? We got one more. One more in us. Yeah.
So when I was solving this, I kind of like had a mental whatever.
Luck.
And I completely forgot what we were solving for. So I accidentally tried to solve for work in the first part, and I got 0.88, but I'm not sure if it works because for the we have the
You have delta x. You know the cosine of theta.
and then I just for the force I just did mass times acceleration.
That would work.
Alright.
I didn't
I just want to make sure I wasn't accidentally it was just a fluke or something.
Yeah. That works. Tommy.
I'd like the notes for work non-conserved.
Yeah.
It says not to use it with gravity, because it's not considered a problem. Or what does that mean when it says don't use work with gravity?
So only use when gravity and springs are the only forces. Use if there are other forces besides gravity and springs. So here we're probably, that's what I'm thinking. Here, the only thing I can think of is air resistance.
Oh, okay.
So the work non-conserved is air resistance.
It's free fall.
Correct.
Okay, thank you.
And then it makes
All right, let's do one more. One more. Little diver. Any swimmer divers in here?
Well, I used to.
Nice.
Landon, you died.
No, I just went.
Oh.
Very good.
Swimming instructor.
Okay, so
That's
I
pretty
haven't seen the whole.
I mean, you say that like it should be common knowledge.
here we go.
Have you had any kids die on you or not?
No,
Oh.
I don't have a job.
But you said like he's swimming.
That's
All
why
right.
I was a swim instructor. No, so they both died.
One more, guys. One more. Let's
Yeah, but you
plug
were
through
good
this.
at
A 95 kilogram diver steps onto a diving board and drops into the water that is 3 meters below.
Got you there.
Okay.
Hold on, no, I'm waiting.
It makes it easier. It makes it easier to spell.
So, at depth D, below the water's surface, the diver comes to rest. Okay, what is depth D? Okay, so we know that, I'm going to draw it out real quick so we can see it. So we know that here's the diving board. I'm going to call this the diving board. Here's the line of water. So we know from here to here is 3 meters. We're trying to find how far he goes down here, right? So, once again, you guys ready for this? This is going to be my last one doing this.
So pumped.
Kinetic energy initial plus potential energy initial plus elastic potential energy initial plus work non-conserved is equal to, I'm going to take a shortcut. Is he going to have kinetic energy when he comes to rest in the final?
No.
He's not going to have kinetic energy. Is he going to have potential energy if he's at height of 0? No. Is there elastic potential energy in this problem?
No.
Is it all right if I just took the shortcut? So all that's going to be equal to 0. Okay. Let's see. In this problem, let's see. Initial. He has initial potential. Does he have initial kinetic? No. And there's no springs involved.
I enjoy this. I like to see a lot of X's.
Okay, so if we see this, I still have potential because he's on the diving board. Okay, so mass times gravity times height. So what's my mass? 95 times gravity times the height. Okay. And let's see. And then, so we don't know the height actually above 0. So that's what we're actually solving for. Plus the work non-conserved, I think I'm given that, which is, oh, we got a negative 5.20 is equal to 0. Okay. Yeah.
Negative 2,327 is not 0.
Homie, what?
Bro, we already established 0.
Did you just tell me?
I did.
Like over here, there's no kinetic, no potential, no elastic potential.
You already have height though.
The height above the water, we're trying to find depth D. So we're trying to find what D is. Depth below water. Okay. So what is my H?
5.5.
You say 5.5? Yeah.
Yeah.
Okay. I was just saying.
I
So
do check it. It's like
5.5. So 5.5 is the total off the diving board to where he's at on his feet. So how deep did he go in the water is the question. 2.5 would be your answer.
Okay, that makes sense.
Okay, this is the easiest thing that we've done.
Question.
Well, why is there no final kinetic energy on this one, but there was on the last one?
Because at depth below the surface, let's see, and drops it at depth D below the diver comes to rest. So here he comes to a rest on the last question. Deep and falls straight to the ground if the initial and its speed on landing. So if this has a final this has final kinetic energy. Like we know the velocity. We're calculating the velocity right before it lands. Where on this, on the diver one, he comes to a stop. Does that kind of make sense? All right. That is work non-conserved. Now there's more problems, and if you want to go practice the more problems, that would be fantastic. I will go over each one if you want me to.